Finding higher order derivatives. Our objective in this lesson is to find higher order derivatives and work with acceleration. Our notation for derivatives: for y equals f of x, if we say the first derivative of f, we can use prime notation, which would be y prime, or f prime of x. The second derivative of f would be y double prime, or f double prime of x, and so on and so forth. The third derivative of f would be y triple prime, or f triple prime of x. Once we get to fourth derivative and above, we use what looks like an exponent, but notice that there's the parentheses around the 4. It's different from an exponent. So we stop using that prime notation and go with y to the, in the parentheses 4, meaning fourth derivative of y, or f fourth derivative. So in general, the nth derivative of f would be y to the, in the parentheses n, or f to the, in the parentheses n, of x. Anything 4 or higher gets written like an exponent, but we know it's not an exponent because of the parentheses. If we choose to use Leibniz notation, we're saying for the first derivative, dy dx, which of course means the derivative with respect to x of y, or the derivative with respect to x of f of x. Now if we take the second derivative of f, notice that we're taking the derivative with respect to x of the derivative with respect to x of f of x. So notice how we have d and another d. That's what makes the d squared, and a dx and another dx, and that's what makes the dx squared. So hence the notation of d squared y dx squared for the second derivative of the function y in Leibniz notation. It continues down for third derivative, fourth derivative, and anything higher as well. Operator notation looks similar, but we don't generally use it much. Applying higher derivatives would be for position, velocity, and acceleration. For an object in rectilinear motion whose distance s from the origin at time t is s equals s of t, we remember that velocity means the rate of change of position with respect to time. Therefore, v, or v of t, v as a function of t, equals the derivative of position with respect to time, or ds dt. Acceleration is the rate of change of velocity with respect to time, usually denoted with the letter a for acceleration. So a as a function of t will be the derivative of velocity with respect to time. D dt, the derivative with respect to time of velocity, which is the derivative with respect to time of the derivative of s with respect to time, or the second derivative with respect to time of the position function. Let's look at some examples. 1. Find y double prime, y triple prime, and y fourth derivative for y equals 2x cubed. To get to y double prime, the second derivative of y, we first need to find y prime. Using our power rule, that makes 6x squared. We remember that y double prime means I'm doing the derivative of y prime. So the derivative with respect to x of y prime means I'm doing the derivative with respect to x of 6x squared, and using the power rule, that's just 12x. Y triple prime means I'm taking the derivative of the second derivative, and the derivative of 12x is 12, and then the fourth derivative of y, because 12 is a constant, is 0. A ball is propelled vertically upward from the ground with an initial velocity of 29.4 meters per second. The height s in meters of the ball above the ground is approximately s, or s as a function of t, equal to negative 4.9 t squared plus 29.4 t, where t is the number of seconds that elapse from the moment the ball is released. A. What is the velocity of the ball at time t? What is its velocity at t equals 1 second? Well, we remember that velocity is the rate of change of position. And if it's at one instance in time, that's the instantaneous velocity, which is the derivative of position, or s prime of t. So using our power rule, we take the derivative of the s of t function. We get negative 9.8 when we multiply by 2, t to the first power, plus 29.4, and then there's no more t, 29.4. This is the velocity at any time t. To answer the second part of the question, what is the velocity at t equals 1 second, we're finding the velocity when t is 1, so we're plugging 1 in for t into that function. Negative 9.8 times 1 plus 29.4. That makes 19.6, and because our problem is about a scenario, it has words, we have words in our answer. Velocity is the rate of change of the position, meters, with respect to time, so meters per second. B. When will the ball reach its maximum height? So if we think about what happens when a ball is thrown, when it gets to the top of its path, it's going to stop for an instant before it comes back down. Therefore, the velocity at that instant will be 0. Remember up here we found the velocity function. So negative 9.8 t plus 29.4 equal 0 will help us figure out the time. Subtracting 29.4 and then dividing by negative 9.8 gives us t equals 3. And of course, being a problem with words, we give our answer with words. When will the ball reach its maximum height? We'll answer at 3 seconds. C. What is the maximum height the ball reaches? Well, we know the ball reaches its maximum height at 3 seconds, and the position is given by this function in the problem. So we want the position at 3 seconds, plugging 3 seconds into the position function. Negative 4.9 times 3 squared plus 29.4. That gives us, times 3, which makes 44.1. And again, being this is a scenario, there are words, we have words in our answer. This would be m for meters. D. What is the acceleration of the ball at any time t? That's at one point in time, that's a derivative. Acceleration, often called a, is the rate of change of velocity, v prime of t. So I look up here to where we have our velocity function and we take the derivative of the velocity function. That would give us negative 9.8. Again, this is a scenario, it has words, so we have words in our answer. The acceleration is negative 9.8 meters per second squared. If we're not sure what the units are, let's remember that acceleration means the change in velocity over the change in time. The velocity units are meters per second, and the time units are second. So that makes meters per second squared. E. How long is the ball in the air? Well, if we think about what's happening, a ball is being thrown upward from the ground. So how long is the ball in the air? We're looking for a t value, and we're looking for it from when the position started at the ground until the position reaches the ground again. So we're trying to figure out where is the position function equal to 0, or rather, when is the position function equal to 0. So if we take our position function, negative 4.9 t squared plus 29.4 t, and set it equal to 0, we can do some solving. T factors out to give us negative 4.9 t plus 29.4 equal to 0, which gives us two values, t equals 0 and t equals 6. Those are the two times that the position of the ball is on the ground, or the position equals 0. Well, of course, the position is 0 at first because the ball was thrown upward from the ground, but t equals 6 is when the ball hits the ground again. So how long is the ball in the air? We answer the question with that second t value, 6 seconds. F. What is the velocity of the ball upon impact with the ground? Impact meaning when it touches the ground. We have a velocity function that we found in Part A, and we know when the ball impacts the ground, at 6 seconds. So we want to find the velocity at 6 seconds. Taking our velocity function, we'll plug 6 into that. Negative 9.8 times 6 plus 29.4. That makes negative 29.4. And our units for velocity are meters per second. That's the velocity of the ball upon impact with the ground. What about the speed? The speed is the velocity, but without the sign. The speed is the absolute value of the velocity. Velocity is speed with direction, the negative meaning that the ball is going down or getting closer to where it started. The distance is decreasing. So the speed of the ball is 29.4 meters per second. G. What is the total distance traveled by the ball? So we know that the ball goes up for 3 seconds and then hits the ground after 6 seconds. So thinking about its position, S of 3 at 3 seconds, plugging the 3 into the position earlier gave us 44.1 meters. It goes from the ground to get to its maximum height of 44.1 meters, and then it comes back down for 3 more seconds. So it traveled a total of 44.1 meters plus 44.1 more meters to make 88.2 meters. Thanks for watching.